Section 5. The quality of the data analysis. This is about FAPAS as a proficiency testing provider and what we do to ensure that you get the best assessment of your data possible. The assessment you receive is in the form of a Z-score. This includes the participant's result, the assigned value, and the statistic sigma p, which is the standard deviation for proficiency. This section of the webinar looks at how we derive the assigned value and how we derive the standard deviation. First of all, we need to decide which of the results we include in the assessment of the assigned value. In other words, which values are valid for the calculation and which are not valid and excluded from that calculation. All results will still get a Z-score, but not all will be included in the calculation. In this example, we've excluded 4 of the results. The result at the top, 1.432, is clearly not part of the population. The assigned value is 1404, so this result is clearly not in the same order of magnitude as all the others. The next 3 results have also been excluded, even though at least 2 of them are not very different from the assigned value. Why is this? Part of the instructions is that we require in this analysis acrylamide for results to be corrected for batch recovery. For these 3 results, participants stated that they were not corrected for recovery. Therefore, they are not valid for the purposes of our calculation. You will see in our reports and protocol that we refer to robust statistics, in particular the robust mean. What does this mean? If we have a set of data represented by this graph and the blue bars on the graph, we could calculate a simple mean value, but we see to the right hand side there are some outlying data points. We could use exclusion criteria, some kind of outlier test, but the thinking in the statistics is that it's preferred to use a robust method instead. And so we use a robust algorithm that reduces the effect of those outlying data points. In practice, this means that an arithmetic or simple mean is affected by the outliers. In this case it gives a value of 8.11, but a robust mean gives a more correct or accurate value of consensus, which is representative of the majority of participants, and in this case it's different at 7.82. We might also get multiple populations of results. We use an adaptive kernel density estimation to find out if we have a multimodal distribution. Informally, this is called bump hunting because we're looking for bumps in the distribution. These may be error related or they might be method related, and it's important to try and establish what is the cause of this so that we choose the correct mode in the dataset. The standard deviation for proficiency must be objective and it must be prescriptive. This means we must know before the PT what is going to be acceptable for the analysis in question. It's not the same as the observed standard deviation of the data. That's a different kind of standard deviation. Where do we get these values from? Well, we might use predictive models, values from interlaboratory reproducibility, typically collaborative trials, or we might use expert judgment where none of these are suitable. They might be defined in legislation. The Horwitz equation is used for the majority of contaminant analyses in food chemistry. This is the original Horwitz equation, and if you describe this as a graph, you get the Horwitz curve. It's a remarkable equation, and it works for most analyses at most concentrations most of the time. So you will see this commonly used in FAPAS reports. However, the original Horwitz equation begins to fail at very low concentrations and at very high concentrations. At low concentrations, this is less than about 120 parts per billion, what we observe is that the Horwitz equation is not appropriate, and in fact reproducibility levels off at about 22%, which is the red horizontal line on this graph. This effect was described by Professor Michael Thompson, the author of, or co-author of the International Harmonised Protocol for Proficiency Testing. There is a similar effect at high concentrations, more than about 13.8%, so this might be sugar in high sugar products, for example, where a further modification of the Horwitz equation was also described by Thompson, and the graph is quite different. Does the Horwitz equation still work? The original Horwitz equation is nearly 40 years old, so is it appropriate to use it? Work by Professor Thompson and colleagues at FAPAS produced this graph, where the coloured lines are the actual FAPAS data from 2009, 2010 and 2011. The original Horwitz function is described by the curved dashed line, and the horizontal dotted line is the Thompson modification. The fit of the observed data to theoretical data is remarkable. So yes, the Horwitz equation does still work. We assume that distributions are normal. However, there are evidence of non-normal distributions. Microbiological results have long been known to be not normally distributed. They're often described as a Poisson distribution. So we can modify our statistical approach to compensate. Similarly, GM analyses are also non-normally distributed, and we apply the same correction as for food microbiology. The correction is to log transform the raw data. So you will see in our reports the z-score equation is modified with log 10 values instead of absolute values. In water microbiology, the transformation is not a log transformation but square roots, and this derives from work that FAPAS has done on its own microbiology PT data.